In this lecture, we're going to learn the third substitution method called the Bernoulli equation. So this is the third method called the Bernoulli equation. Bernoulli's equation. Bernoulli's equation. So this is actually, there were three famous Bernoullis in sciences. So this is the one called the Jacob Bernoulli. Okay, so Bernoulli equation. So what's the Bernoulli equation? So before we talk about the Bernoulli equation, so let's kind of recall what we did with the first order linear differential equation. So remember, we were talking about this kind of equation. So what is that? So y prime plus px y equal qx. So if you get this kind of differential equation, hope you remember what we did. We find what we call the integrating factor. So we find I equal e to the px dx. So this is what we normally call the integrating factor. So we write this one as integrating fact. Okay, and then what's the next step? We're going to multiply the whole equation by the integrating factor. So it is I y prime plus px I y equal I, this is also function of x, so iq. And then what we're gonna do, when you do that, the left side is automatically becomes the derivative of I times y. So that's the automatic situation. And then we have iq on the other side. Okay, after that, what we do, we're going to integrate both sides. Once you integrate both sides, this side becomes iy equal the integral of iq. So these both are functions of x, and then so it's going to dx. And then once you finish the integral, so you're going to integrate this side. So we normally assume that this is something like easy to integrate. So easy to integrate, and then we can solve for y by dividing by I. Okay, so this is what we normally call the integrating factor method. So the last step is we have y, you're going to divide by I, so it's 1 over I, the integral of I q dx. Normally there's a c here, so we normally write it like that, with the explicit c in there, because you have to divide the whole thing by I. Okay, so this is the what we call the integrating factor method. So now let's consider the general case. So what's the general case? Not really the general case, but the current next step. So so consider this equation. So what is that? Y prime plus px y equal some function of q and then yn, like that. So you consider this kind of equation. This is what we normally call the Bernoulli equation. So this is what we call the Bernoulli equation. See the slight difference from the first order linear. So you can have that q to the n term. So that's the difference here. I'm sorry, y to the n term. So that's the difference here. So this is what we call the Bernoulli equation. Bernoulli's equation. So now let's see how we do this. So let's talk about few cases. So for example, if n equals 0, so if n equals 0, your equation becomes y prime plus p x y equal qx. So this is simple first order linear, so integrating factor method. So we can apply for this one, you can just use the, so this is first order linear, so we can use the integrating factor method for this one. So we can do that. So if n equals 0, just a basic first order linear. Now let's see if n equal 1. If n equal 1, what will happen? So it is y prime plus pxy equal qxy. So if this is the case, now we can actually do this problem in two different ways. So the first method is you can move the pxy term to the other side. So the first method, so we can move this term to the other side and then factor y. So you can write this one as qx minus px times y. So you can do that. So if we do that, this is just a separable equation. You can see this is separable. It's just separable. Or you can move qx term to the other side. So or you can write like that. So it is y prime plus, if you move this term to the other side, so it's going to be px minus qx y equals 0. So if we do that, this is first order linear. That means the integrating factor method. So this is the first order linear. So so we can use the integrating factor method. So that means those two cases you can consider separately. So if n equals 0, it is simply the first order linear, so it uses integrating factor method. But if n equal 1, you have two ways to do this problem. So if you can move px term to the other side, if you do that, it's going to be separable equation. But if you move qx to this side, it's going to be integrating factor method. So there are two ways to do n equal 1 case. So now, so let's assume that n not equal to any of those two numbers. Okay, so that's the case we're going to consider now. So let's say n not equal to, so if n are not equal to either 0 or 1. So that's a special case. So let's consider the problem again. So we have y prime plus pxy equal qx y to the n. So we know the n not equal to 0 or 1. Now what we're going to divide by this special term. So that is the trick. We're going to divide by that term both sides. Okay, we're going to divide by that. So if you divide by that, so divide. Okay, so dividing by y to the n, whatever the term, just divide by that. If you divide by that, what's going to happen here? This is going to be y prime over y to the n plus px y over y to the n. So this side simply becomes qx. So you can rewrite this one as y to the minus n power y prime px. So here also there's a simplification. So this is y 1 minus n power, because there's a 1 on the top and then n y to the n in the bottom. So you're going to get that. So this is qx. Now the interesting part. So what we can do, we're going to make a special substitution right now. So we can substitute for this term right here. We're going to substitute for that term. So we're going to call this term is v. Okay, so that is the special substitution we're going to use for this one. So we're going to say let v equal y to the 1 minus n. Okay, so that is the special substitution that we're going to use for Bernoulli equation. It is always v equal y 1 minus n, always. Now what we can do, we can take the derivatives of both sides. So we can take the derivative of both sides. So if you want to take the derivative, be careful, because y is a function of x, so that means you have to use a chain rule. So what do you get? So we're going to say differentiate with respect to x. So that means you need the chain rule for that. So that means dv over dx. First we know that v is a function of y, so that means dv over dy times dy over dx by the chain rule. So if you do that, what do you get? In this case, we're going to get v prime. If you take dv over dy, you're going to get 1 minus n to the y, you're going to subtract 1, so that means you're going to be minus n. dy over dx means y prime. So that's what you get when you take the derivative. But what we're going to do, we can divide both sides by 1 minus n. Okay, so that means if you divide both sides by 1 minus n, we're going to get v prime over 1 minus n y minus n y prime. And this is also a formula because you need that in the substitution. You can see that this right hand side is exactly sitting in the equation. You see that this right hand side is the exact term here. You see that those two are matching, so that means we can substitute for that. So that's exactly what we do, because those two terms are exactly the same, so we're gonna substitute for that. So then once you substitute, so I'm gonna call this equation star. So this equation becomes now, so then the equation star becomes, we can substitute the first term, so it's a v prime over 1 minus n plus px, and we know that the y to the 1 minus n is v equal on the other side qx. Okay, now you can see that this is simply the first order linear equation. This is first order linear equation, so we can use the integrating factor method to solve this. Okay, so this is first order linear, so we can use the integrating factor method to solve for v first. After we solve for v, we can substitute v equal y to the 1 minus n to solve for y. Okay, so so let's write it in Word. So what we're gonna do, so use integrating factor method, integrating factor method to solve for v, and then use v equal y to the 1 minus n to solve for y. Okay, to solve for y. So that is the kind of technique we're going to use for Bernoulli's equation. So again, if you go back, so let's see what we did. So we start with y prime equal px y equal qx y to the n. We divide both sides by y to the n, and we can assume that n not equal to 0 or 1. And once you do that, you're going to get the star equation. It is y to the minus n y prime plus px y to the 1 minus n qx. And here we can use the special substitution. We always gonna see that y to the 1 minus n term. So if you see y to the 1 minus n term, we gonna let this as v and then take the derivative. Once you take the derivative by the chain rule, you're gonna get v prime equal 1 minus n y to the minus n y prime. You can divide by 1 minus n both sides, then you're going to get v prime over 1 minus n equal y to the minus n y prime. And you can see that what is on the right hand side is exactly the first term of the star equation. That's exactly the first term, so we can substitute for that. And once you substitute for that, you're going to get this equation. So this is v prime over 1 minus n plus pxv equal qx, and this is exactly the first order linear equation in v. Okay, so first order linear in v. So what we can do, we're going to solve this equation using the integrating factor method. So we're going to solve this first. So we use the integrating factor method to solve for v first, and then we use v equal y to the 1 minus n, the substitution, to solve for y. So let's look at about 2-3 examples. So let's start with something easy first. So this is the first example. So example 1. So let's say solve dy over dx plus 2y equal y squared. So once you look at this equation, you can see that we have this special term, this term. So because of that term, you know that this is Bernoulli. Okay, so that's the first thing you need to understand. This y squared term make it Bernoulli. This is a y term, you can bring it to the other side and it just become a first order linear. But because of this y squared term, this is this is the Bernoulli. Okay, so let's finish the argument now. But also you notice that y equals 0 is a solution right now. So since y equals 0 is a solution, so we're gonna remove that case first. So first note that actually not just y equals 0, because you can move the two y terms also to the other side. Once you move the two y terms to the other side, what's going to happen? Let's see what's going to happen if you move the both terms. If you move both terms, it's going to be y squared minus 2y. So this has factors y minus 2, and you can see that if you plug in any of them, y equals 0, y equal 2, so this says that y equal either 0 or 2, you can see that both of them are solutions for this differential equation, because if you plug in them, the two sides become equal and the derivative is 0, so that means those are solutions. So let's exclude them first, because they're going to create problems. So first note that y equal 0 and 2 are solutions. These are what we call singular solutions. Okay, so and then we're going to make the assumption that, so assume that y not equal to 0 or 2, and divide the whole equation. So divide the differential equation by a y squared, because that's the term you're going to see on the other side. So we can divide by y squared. Okay, so that's the term sitting on the other side. We can divide by that term. Good. So if you divide by that, what are you going to get? You're going to get 1 over y squared dy over d. I might write some extra step because it's the first example, but later I'm going to skip this step actually. So this is, and then you're going to have 2y over y squared, then it'll be 1. You can rewrite this equation as y to the negative 2 and then y prime plus 2 y to the, if you bring that to the top, it's negative 1 equal 1. So that is the equation that we get when you divide by y squared. Now we know what to do. Okay, so what we do next, we're gonna substitute for this term. Okay, whatever that term, you're gonna substitute for that. So in this case is y to the negative 1. So let's make the substitution. So let v equal y to the negative 1. Okay, and then taking derivatives, we're gonna have v prime equal dv over dy over dx. You don't want to write this one again and again, because if you remember what to do, just go ahead and do it. This is negative y to the negative 2, that's the first term, and then y prime. Okay, And then this says that if you solve for y to the negative 2y prime, because that's the first term that you see in the equation, is negative v prime. So you have to do that. Okay, so y to the negative 2y prime is negative v prime. Now what we can do, we can substitute that in the equation. So so we can say then your equation becomes negative v prime plus so what we had, your p is 2 and then this is v equal 1. So that's the equation you're going to get, negative v prime plus 2v equal 1. Now you can see that this is the first order linear in v. Okay, but we still make some changes. We're going to multiply by negative sign first, so we can write this one as v prime minus 2v equal negative 1, and then you can see that this is a first order linear. Okay. So first order linear, so we can use the integrating factor. Okay, first order linear in v, actually in v, so we can use integrating factor method. So let's finish the rest of the work. So the integrating factor is e to the integral of px dx. So e to the integral of negative 2 dx. So e to the negative 2x. Okay. And then what's going to happen? So then what's going to happen? This is d by dx, e to the negative 2x, that's the integrating factor, times v. So times v, okay, so v times v equal, so we have negative e to the negative 2x. Now what we're going to do, we can integrate. So on to integrate, we're going to get v e to the negative 2x on this side, and here the integral of e to the negative 2x dx. So this is a very easy integral, you can divide by the constant. We have done this several times, and if you use the 4 formula, you can see this. So this simply becomes 1 over negative 2 e to the negative 2x plus c. This you can simplify, you're going to get 1/2 e to the negative 2x plus c. So this is simply coming from the 4 formula trick. Okay, we use this a lot. There's a video, you can see that in the channel. Good. And then what we can do, we're going to multiply by e to the negative 2v. So then once you multiply by e to the 2v, actually e to the 2v, so it's going to be 1/2 plus c e to the 2x. Now we know that y is v equal, what is the negative one? So you can say since v equal y to the negative 1, this is y to the negative 1 equal 1/2. So you can just take the common denominator. So it's 1 plus 2c e to the 2x over 2. So what we're going to do is we're going to make it upside down and write the solution as y equal 2 over 1 plus, actually for the 2c you can just call it just 1c because it's just a c, so I'm going to call it just c. So c e to the 2x, so as the solution. And then if you are given any initial conditions, now you can use the initial conditions to find the c. Okay, for example, you can say that y0 equal 1. If you say y0 equal 1, you can see the c equal 1. Okay, so likewise, you know, if you see any initial conditions, you can use them to find c. So I'm going to write that here. Okay, so use initial conditions to find c, if any. Okay, so if they are not given, then you cannot do that. Okay, for example, if you say y0 equal 1, you're going to see the c equal 1. Okay, something like that. Good. So but this is the whole problem, and you can see that once you solve for v, we can use a substitution to solve for solve for y. Okay, so but first you need to solve for v. First you solve for v, and then we can substitute this and then solve for y. Okay, let's do more examples. So how about another example? So let's do another one. We need one more step. So how about this example number 2? Solve. Let's say x dy over dx plus y equal x squared y squared. X squared y squared. Okay, so if you look at this problem, as before, you identified that there's a y squared term. That y squared term makes this a Bernoulli type of equation. Okay, so that's the first thing you notice. You notice that there's a y squared term, so that's gonna make it a Bernoulli type equation. But there are a few things to do here, because you see that you need to divide by y squared, that one thing, but also you notice that there's an x term sitting there. So that means you have to divide by both. So what we can do, we can divide by the product of those. Okay, so again, so let's say as before, we're gonna make the assumption. So we say first, note that y equals 0 is a solution, is a singular solution. Good. Okay, it's a singular solution. So and then so what we can do is we can assume that y not equal to 0. So assume y not equal to 0, and you can see that because if y equals 0, you cannot divide by 0. So that's why we need to make this assumption, because otherwise this argument is completely wrong. Okay, and then divide by, you can say dividing by the product x and y squared, because you need to take the x term out and also the y squared term out. So we can divide by both. So once you divide by both, what's gonna happen? You're gonna get y to the negative 2 dy over dx plus the x term come down, so it is 1 over x, and also this can be y to the negative 1, and here 1x get cancels and y squared term is gone. So this is what you get. Okay, once you divide by x y squared, you're gonna get that. Now the substitution. So what's the substitution? We're gonna pick this term. Okay, so let's substitute. So let v equal y to the negative 1 as before. Taking derivatives. Okay, taking derivatives, we can have y prime equal negative y negative 2 y prime. In other words, y negative 2 y prime equal negative v prime. So we can substitute. So once you substitute, so we can say, I'm going to call this star because it's easy. So substituting in star, you can get negative v prime plus 1 over x v equal x. Multiply by the negative sign, so you write this one as v prime minus 1 over x v equal negative x. Now the integrating factor I equal e to the px dx. In this case, e, you have to take the whole term, so it is a negative 1 over x. So negative 1 over x dx. Remember, you have to take the whole term, okay, because there's a negative sign, so we're going to pick the whole term as p. Good. So negative. So if you integrate this in negative ln x, we don't write the absolute sign here because we're looking for one solution. bring the negative sign inside, so that means this is e ln x to the negative 1. This term get cancelled, so you get x to the negative 1 or 1 over x. Okay, so that is the integrating factor. So we're going to multiply by that. So once you multiply by that, you're going to get 1 over x v prime minus 1 over x squared v equal negative x 1 over x, that means negative 1. Now you can see that this is, by the theory, this is just the product of the integrating factor and v equal negative 1. So what do you do? Integrate both sides. Okay, so once you integrate both sides, you're going to get, so integrating we're going to get 1 over x v equal the integral of negative dx. This is negative x plus c. Now we're going to multiply by x both sides, so we're going to get v equal negative x squared plus cx. Now we're going to use a substitution, so we solve for v, so that part is done. Now since v equal y to the negative 1, y equal negative 1, we have y negative 1 equal negative x squared plus cx. And then what we can do, we're going to make it upside down. So this gonna say is that y equal, so let's say y equal, if you make it upside down, 1 over, we write the positive terms first, and x squared. So that is the general solution. And again, if you know the initial condition, you can solve for C. Okay, good. But this is not the general solution, because remember you have this solution and the y equals 0 solution. Okay, so the general solution is y equals 0 or this. Okay, good. So let's do one with the initial condition. So we didn't do anything with initial condition, so let's try to do another one with the initial condition. Yeah, good. Yeah, so I will probably do like 2 more examples just to practice, but otherwise the theory is over. So this is just extra examples. So example number 3. So solve the initial value problem. Let's say y prime plus 4 over x, y equal x3 y squared. I just put square every time just to see, just to compare what's going on. Okay, so and then let's say y2 equal negative 1 over 16, and assume that x is positive. Okay, so let's see how this gonna work. So we know what to do now. We can divide by y squared. Okay, so again, so we first check whether y equals 0 is a solution. Okay, so note that we can see that there's one solution. Okay, so note that y equals 0 is a solution. So assume that y not equal to 0 and divide the differential equation by y squared. Why y squared? That's the term sitting here. Good. So once you do that, you're gonna get y to the negative 2 y prime plus 4 over x, and when you divide by y squared, this can be y to the negative 1. This can be x to the cube. Now this is the term that we have, so we're gonna call this term v. Okay, we're gonna call this term v. So let v equal y to the negative 1, and we're gonna take the derivative. Once we take the derivative, v prime equal negative y to the negative 2 y prime. This is gonna say that y to the negative 2 y prime equal negative v prime, and we're gonna substitute. Once you substitute that in the equation, it's gonna be negative v prime plus 4 of x v equal x to the cube. And then we can multiply with negative sign, so v prime equal 4 over x v equal negative x cube, and you can see this is Bernoulli. This is just the first order linear. This is just a first order linear. First order linear, so integrating factors. Good. So let's try and find the integrating factor. So integrating factor I equal e to the px dx. So in this case, e to the px is negative 4 over x dx. This is a very easy integral, so it's a negative 4 ln x that we're going to bring inside. So you're going to see e to the ln x to the negative 4. This get cancelled, so you're going to get x to the negative 4. And then multiplying by x to the negative 4, you're going to get x to the negative 4 v prime minus 4 x to the negative 5th v equal negative x to the 3 times x to the negative 4. This is 1 over x, negative 1 over x. Now by theory we know that this side is automatically the y, not the y, v and the integrating factor. V and the integrating factor is x to the negative 4. That's automatic, and you can even check. And then we have negative 1 over x. Now we can integrate. If we integrate, we're going to see v x to the negative 4th, the integral of 1 over x dx, which is negative ln x plus c. Now we're going to multiply by x to the negative 4th, and also we can substitute for v. So v equal, if you multiply by x to the 4th, negative x to the 4th ln x plus c x to the 4th. Okay. Now we know that the v equal y to the, so we can say since v equal y to the negative 1, we have y to the negative 1 equal x to the 4th if you take x to the 4th as a factor, you can see c minus ln x. So we can write it like that. Now what we can do, so that's a solution. That's a solution. But now what we can do, we can use the initial condition. Okay, we can use the initial condition. So we say we can use y to the 2 equal negative 1 over 16. So we can use that. So that means, so what will happen, your equation is y to the negative 1, so that we can negative 16, and if you plug in x equal 2, this becomes 16, c minus ln 2. So you see that 16 get cancelled, so this can give you c equal ln 2 minus 1. 1 means e. I mean, you can leave it like that, or you can do some kind of interesting simplification, because 1 is ln e, so you can write this one as ln 2 over e. Okay. Just 1, and then so the solution now simply becomes y equal, because you have to make it upside down, so it's a 1 over x to the 4th. We can substitute, so the constant become ln 2 over e minus ln absolute value x. So if you combine all of them into 1, so you're going to see 1 over x to the 4th ln, you can see 2 over xe. So we're going to put that. So that's the solution to the initial value problem. So so we have done 3 examples, so maybe just do one more, just for extra practice. There's nothing new here. So this is the last example. So this is example number 4. So solve the initial value problem. Y prime equal 5y plus e to the negative 2x, y to the negative 2, and then also y0 equal 2, something like that. Okay, so there's nothing major here, so that's the term, so you have to divide by that, and then you can see that y equals 0 is not a solution now, so you have to be, because you cannot plug in y equals 0 now. So we know that y not equal to 0. Good. Okay, so the answer, so we're gonna see, we can divide by y to the negative 2. So divide by, so dividing by y to the negative 2, we're gonna get, when you divide by y to the negative 2, that means you multiply by y squared. So your equation becomes y squared y prime, and also you can bring the 5y term to this side and then divide, so it's going to be negative 5y cubed now, and this side is e to the negative 2x. So this step is clear now, because I move the 5y term to the other side to bring it to the right format, and then divide by y to the negative 2. Now we know what's the substitution. So the substitution is this, so we're going to pick that as v. So let v equal y cube. Okay, and then we're gonna take the derivative. Once you take the derivative, this is v prime equal 3 y squared y prime, and you're gonna see that y squared y prime is in there. So this term is there, that term exactly matches that term. That's always the case for this type of differential equation. So that means you can solve for that. So that means y squared y prime is 1/3 v prime. So that's what we can substitute. Okay, so we can substitute that. So once you substitute that, so substituting v prime over 3 minus 5v equal e to the negative 2x multiplied by 3, so we can see v prime equal negative 15v 3e negative 2x. This is just the first order linear. So integrating factors. So I equal e to the px dx. E to the px is negative 15 dx. So e to the negative 15x. So that's the integrating factor. So we're going to multiply the whole equation by that. So then we have your equation, as d over dx. You first multiply by that, so we can write this one as now v e to the negative 15x, and then this side is 3e negative 2x times e to the negative 15x. Okay, good. So you can simplify this one, so this is 3e to the negative 17x. Oh, sorry, get. We can integrate. Okay, so we can integrate. Once you integrate, you're going to get v e negative 15x equal 3, the integral of e to the negative 17x dx. This is again a very easy integral. The 4 formulas, I'm going to write the formula here now. So if you have e to the kx dx, integral is simply 1 over k e to the kx plus c. We can use that formula here. So that means it's going to be negative 3 over 17 e to the negative 17x plus c. Now we're going to multiply by e to the 15x both sides. So you can say since v equal y cube, we can write y cube e to the negative 15x equal negative 3 over 17 e to the negative 17x plus c. So and then we can multiply by y and take the cube root. Also you can use the initial condition now. Okay, so just to find c, so we're gonna say so we're gonna use the fact that y0 equal 2, and if you do that, then you're gonna get, what do you get? 2 to the cube e0 equal negative 3 over 17 e to the 0 plus c. If you solve for c, what do you get? 2 to the 3 means 8. 8 times 17 means 136. At 3, 139. So it's going to be 139 over 17. Okay, so that's the c. And then now what we can do, we're going to multiply by e to the 15x. So you're going to get y3 and take the cube root, so you're going to get y. Okay, so we have only two more line. So we have y3 e to the negative 15x equal negative 3 over 17 e to the negative 17x plus 139 over 17. So we're going to multiply by e to the 15x, opposite sign. In y3 equal negative 3 over 17 e to the negative 2x plus 139 over 17 e to the 15x. So we take the cube root. Once you take the cube root, and write the positive term first, e to the 15x minus 3 over 17 e to the negative 2x, the cube root. Okay, so that's the solution to the initial value problem. Okay, so I'm going to give you two problems for you to try. So this is so solve the first one, 6y prime minus 2y equal x y to the 4th along with y0 equal negative 2. And the second problem is y prime plus y over x minus square root y equals 0 along with y1 equals 0. Okay, so why don't you try those two, and you can find the solution in the description. Thank you. So this is the end of the Bernoulli's technique, or the third method of the substitution method.